let us just do the comparison between the graphical and the analytical for the 2 position synthesis. So, say I have these 2 given. Okay. So, let me just and similarly for, so I have the same problem specified analytically, we will just look at what we do for the 2 cases. So, if I have okay. So, in the analytical case, okay, for a motion generation problem, I would be specified these 2 positions. So, in the graphical case, say this is A2 P2 A1 P1. So, I am given these 2 positions. Okay. The same thing would be specified as the 2 position motion generation. This is graphical, this is analytical. So, in this case I would be given delta 2 and R2 or R1 R2 and gamma 2. Okay, this is given. In the graphical case I would be given these 2 locations as is. Okay. So, the equation that I have here between the vectors I want to find is z power I phi 2 minus 1 plus z2 e power I gamma 2 minus 1 equal to delta 2. 2 position problem, this is the only vector equation I have. Okay. And I know from this table here that I have 3 free choices for the solution, right. I have 2 position problem, I have these are my unknowns z1, z2 and the number of free choices is 3. So, the difference is, so here what the way I exercise my free choices is I pick A1 to be my moving pivot. Okay. If I pick A1 to be, I can pick anything else also. So, I exercise 2 free choices there. Okay. Now, A1 I know in the second location has moved to A2. Okay. So, then I construct the, I know that the corresponding center point or fixed pivot lies on the perpendicular bisector of A1 A2. Okay. So, if I construct the perpendicular bisector of A1 A2, then my third free choice is locating a point on this perpendicular bisector. Okay. So, location of A of moving pivot two free choices I use up there, and then location of the corresponding fixed pivot. Okay. So, I could this is typically called the circle point, right, and the corresponding center point. So, this gives me another free choice. Okay. Same so this becomes OA, and that is how I get this dyad. So, now my dyad is OA, A2, and I already have, I know P2. So, this or OA, A1 and that. So, these are the two things that define one dyad, right. OA, A2 is corresponds to Z1, A2, P2 corresponds to Z2 in the if I look at it as a dyad. Okay. So, that is how I determine the solution for 1/2 of the 4 bar in the graphical method. We know this. In this case, so essentially let me say that my unknowns are Z1, Z2, I also do not know phi 2. Those are my unknowns. Here what I do is I solve for, say I pick Z2, that becomes 2 free choices, scalars. Okay. 2 free choices. Then, so what is Z2 here? Z2 is essentially this vector here, right. So, if I pick Z2, I am saying I am locating this circle point or moving pivot. When I pick Z2, that is what I am doing here, which is the same as my picking A1 in this case. And then I solve, I also have to pick phi 2, so that I can solve for Z1. That is different from the graphical method, because here I can't say that, that is like picking this angle. So, this is Z1, right. So, from this position, okay, to this position, this rotates by an angle phi 2. Okay. That is what I am picking in this case as my free choice. Then I can find the corresponding Z1. What is that vector Z1 that rotates through this angle phi 2, so that A1 moves to A2. So, I am trying to locate this point OA by that means. I am saying where should OA be located such that this Z1, okay, then I can, from this equation I solve for Z1 as delta 2 minus Z2 e power I gamma 2. So, this is less intuitive, right. It is easy for the equation, this is how I solve it, right. So, phi 2 is the other free choice, but phi 2 then this helps me locate Z1. When I solve for Z1, I get this. So, then I am able to locate OA from this, and it is such that it will rotate by phi 2. Okay. Is that clear? So, the number of free choices do not change, what you pick as your free choice changes, okay, and that determines how you solve for the other unknown vector. Okay. So, then you get this becomes Z1. Once I pick phi 2, I can solve this equation. Clear? Okay. Similarly, you can do this comparison for 3 position also, but I will you get the idea. This is basically to illustrate that this is much harder to do here, trying to find something that will rotate through a certain angle. Of course, here you can again it will still involve the same kind of construction, okay, but I could essentially get the same solutions from both the analytical method and the graphical method, okay, and the same number of solutions are also possible. So, we have Z1 e power I phi 2 minus 1 e power I gamma 2 minus 1 equal to delta 2, the diet form, the standard form. So, here, or more generally I can write it as phi j minus 1 gamma j minus 1, right, between j greater than or equal to 2. Sorry. Okay. Now, if I want to solve a path generation problem. So, let us say we are looking at path generation with prescribed timing. What does that mean? Prescribed timing means for a certain input angle, okay, you want the coupler point to be at a certain location. Path generation means you are only worried about the location of this coupler point P at successive positions. You are not really, you do not really care about the position, the orientation of the coupler. You only care about where P is located. With prescribed input timing means if the input angle given a specified given phi j, you have a corresponding delta j. Okay. Every time the input link moves through a certain angle, the path point should move through a certain, should undergo a certain displacement. That is your, so here essentially you will be given phi j and delta j. If you look at the form of this equation, for the motion generation we were given delta j and gamma j. Delta j, gamma j given is a motion generation problem. If you are given phi j and delta j, it is a path generation with prescribed timing. If I am given only delta j, then it is just a simple path generation problem. You do not have any conditions on the input, coordinating it with the input motion. But if you look at this, it is essentially identical because of the form of the equation. This problem is essentially identical to the motion generation situation. So, what do you expect? So, whatever you got, you remember that table that we had, okay? This table, okay? I could essentially reproduce this. So, if I do this, then what changes is that, let me lock this, okay. So, the only thing that changes for the path generation problem is now this is not an unknown, this will be gamma 2. The unknowns will still be Z1, Z2, gamma 2. Here it will be Z1, Z1, Z2, gamma 2 plus gamma 3, gamma 4 and gamma phi. Everything else remains the same. Question?
Why would it consider it to be a function generator?
Which one? This is not a function generation.
But we are corresponding an angle to some output factor. Like some
Input angle to an output angle.
only angles can.
Yeah. Input angle to output angle. That is your function generation. See, every 4 bar has all these relationships. There is going to be a coupler point which fall. The classification is based on your requirement. Ultimately, you are getting a 4 bar. The 4 bar, in the 4 bar you decide that the input output angle relationship is what you want, then you call it function generation. You call it a function generator. If in the 4 bar you are looking at the coupler, its position and orientation, then you call it a motion generator. Same 4 bar, depends on what you want it to do, and you synthesize it accordingly. Okay, the 4 bar still retains all these relationships. There will be points on the coupler which will follow certain paths. The coupler will have certain orientations. Input and output links will have certain angular relationships. That so the classification is entirely based on what you as a designer want. Still a 4 bar. Okay. So here the form remains the same. So the number of solutions, everything for the diode will be the same. So I use the same, so I could essentially use the same code for motion generation as well as path generation with prescribed timing. I am just giving in a different angle in this. Okay. My output is still the diode that I want. Okay. And that again, up to 3 positions you will have a linear system of equations. Beyond 3 positions it becomes a non-linear system, so it is more difficult to solve. Okay. If I did not have phi j, if I only gave delta j, right, then that is your regular path generation problem, just path generation. If I do not coordinate it with phi j, okay, I only care about the coupler point being at certain positions. I do not care how it, in what relation it is to the input link. Then will I have more or less number of solutions for each case? Am I constraining the problem more or less? Less. So what do you expect? You would have more solutions, because again phi j then becomes a free choice. Okay, phi j becomes an unknown, it is not known. So in the unknowns here this goes up. Okay. So you can work that out and see how many positions you can go for a path generation problem where you do not care about the how it is coordinated with the input angle. Okay. So that is that. Now let us look at the next problem we will look at is function generation, and that is slightly different. So this is for one diode. This infinity cube, say for the 2 position problem, is for one diode. So one set of circle and center points. See, because essentially when you design the diode, that is what you are doing. So this is, if this is P, right. So you are essentially minus Z2 locates the circle point, from there minus Z1 locates the corresponding center point. Okay. And these are usually denoted as, okay, circle points. Remember, even in the when we did the slider crank synthesis and we drew the locus of the locations, I designated the circles as k. Okay, that again comes from the this is the circle points are denoted by K, they are called Kreis punct. This is moving pivot or circle point. And this is M. This is easier to remember because it is Mittelpunkt. So, the middle point, that is how I, so it is the center point or fixed pivot. Okay. So, that is essentially what you are doing when you find Z1 and Z2. Okay. You are finding, when you find these two vectors, you are locating the circle point and the corresponding center point. So, this table, when I do it for only one diode, it is for one side of the 4 bar. Again, for the other side, I have the same table. So, if I combine the two, then I have to multiply. So, it is infinity to the power 6, 4 infinity square, the number of choices that I have, okay, for the two diodes that form the 4 bar. Okay. So, now let us look at the function generation problem using this diode synthesis. Okay. So, function generation, what we are doing is we want to correlate prescribed rotations of the input link phi j with rotations of the output link psi j. So, here I do not really care about a coupler point because I am only looking at coordinating the, so if I go phi j So, I could essentially take this as my point P. This is also on the coupler, okay, P in the position 1, and then see how I can set up the, so if this is R1, Rj, delta j. Okay. The angle between these two will be gamma j. So, this if I take it as Z1, take this as Z3, and in my original thing this was Z5. Okay. And this fixed link is Z6. So, I can write my loop closure as, just for the 4 bar, I can write it as Z1 plus Z5 minus Z3 equal to Z6. Then I can write it as Z1 e power I phi j plus Z5 e power I gamma j minus Z3 e power I psi j equal to Z6 does not rotate, it is my fixed link. So, if I subtract 1 from 2, I get Z1 e power I phi j minus 1 plus Z5 e power I gamma j minus 1 minus Z3 e power I psi j minus 1 equal to 0. So, this is not in standard form, this is not in the standard form. Here what would be given? So, the function generation, the given quantities are phi j and psi j, right. I know how they are supposed to table. Number of positions, equations, what are my unknowns, number of scalar unknowns, number of free choices, therefore, number of solutions. Okay. 2 positions. How many equations will I have? I have only 2 scalar equations. Okay. J will be 2. So, what are my unknowns? Practically everything. So, I have Z1, Z5, Z3 and gamma 2, because phi 2 and psi 2 are given. That is the relationship I am designing for. So, the number of scalar unknowns is 2, 4, 6 plus 1, 7. All the z's are vectors. So, I have 7 scalar unknowns. So, my number of free choices is 5. So, I have order of infinity to the power 5. Okay. You should remember that this infinite, it's just to indicate, you know, what are the different infinity to the power 5. Infinity is the largest number possible. So, infinity is not really, it is rather meaningless, but the idea is to indicate how many free choices you have. Okay. So, number of solutions, because each of those infinities corresponds to a different quantity essentially, that is what it indicates. If I go to a 3 position, number of scalar equations now becomes 4. Unknowns are all these, okay, so I will just put a ditto, plus gamma 3. So, number of scalar unknowns is 8, it goes up by 1. So, the number of free choices goes down by 1, you have infinity to the power 4. 4 positions, you now have 6 equations, all these are unknown plus gamma 4, 9, 3. Okay. So, 5, how far can you go before you hit no free choices? 5. So, each time this goes up by 2, but the number of unknowns only goes up by 1. Gamma 5, so 10, 2, 6, number of equations 10, this plus gamma 6, 11, and 7 you have 12, all these plus gamma 7, 12, you end up with 0 free choices, and you may get a maximum of a finite number of solutions. There may be no solution, that is always possible, but maximum you could get a finite number of solutions. Okay. But this again is for the whole mechanism, you are looking at for the function generation, you do not split it into the 2 diodes. Okay. You are looking at the mechanism as a whole. Okay. You can also think of the function generation problem as a special case of the path generation problem, where the path point is the point P1 here on this output link. What is the path of this point? It is a circle, it is a circular path. So, it is a special case of the path generation problem, where this point P is common to the coupler and the output link, and it follows a circular path. Okay. So, this is for the function generation problem. Now, I can rewrite this equation, I can put it in a different form. So, I have this. So, I have the z1 e power I phi j minus 1 plus z phi e power I gamma j minus 1 minus z3 e power I psi j minus 1 equal to 0. Okay. I can rewrite this as plus z phi e power I gamma j minus 1 equal to minus 1. Okay. Now, if I pick z3, if I choose z3 as 2 of my free choices, okay, to use up 2 of my 3 choices, this is of the form, okay, and psi j is known because it is a function generation problem, I am given this. So, this right side becomes of the form delta j. If I choose, okay, picking standard form z1 z phi e power I gamma j minus 1 equal to delta j, where delta j is z3 e power I psi j minus 1. Okay. So, this is now equivalent to the motion generation task or the path generation task. So, what choosing Z3 does is you are basically picking a scale and an orientation for the linkage. Remember, a function generation, because the input and output of the function generation mechanism are internal to the system, internal to the chain, kinematic chain. Okay. So, we have seen earlier that scaling it or changing its orientation will not change the input output relationship. That is what you are doing when you pick Z3. When I pick one of the vectors, so when I pick this, when I specify that, I am essentially specifying the scale of the linkage and its orientation. Okay. So, I can always change that, and it is not going to give me a new mechanism. The input output relation, I mean it will be new in terms of the dimension, but the input output relationship will not change. Okay. So, that is what we are doing here when we pick Z3 and then convert this to the standard form of the diode equation. Okay. So, this is now equivalent to the motion or path generation task. So, choosing, I could have chosen Z1 also, does not matter, one of the two, because I know phi and I know psi. So, if I choose one of these, it gets back to the standard form. Okay. So, choosing Z3 or Z1 specifies the scale and orientation of the function generator. So, once it is synthesized for function generation, it can be scaled up and down or oriented differently, and you will not change the input output relationship. This does not work with motion or path generation, because in motion generation and path generation, the output is external to the system. The output is specified external to the system with respect to some other coordinate system, right. It is not internal to the system as it is in the case of function generation. So, path and motion generators, this is important. The prescribed path will not be achieved if the scale and orientation of the linkage are changed. Okay. So, here changing this does not change the input output relationship. So, that is an important difference between function generators and path and motion generators. Okay. So, we will stop here.